welcome, and thank you for coming and being here. You probably know that cutting tools themselves contribute very little to the part cost. Typically 3%, anywhere from 2 to 5% of the part that you're machining. But the proper use of those cutting tools can save you as much as 40% of that part cost. Typically today we find people are machining too slowly, and therefore production expenses are quite high. Just to illustrate what can be done, if you could in your mind go all the way back to 1969, and if you could imagine that you were involved in the manufacture of some automotive component, imagine for a moment that you were using 200 inserts to machine a part. I don't care what the part is, 200 inserts in 1969. Today, if you were machining that same part, you only need one insert to do it. Improvements in productivity, improvements in cutting tools in particular, have led to that kind of increase in productivity. And we like to see that continue. So cutting tool producers are constantly working on new and better coatings that will allow you to go faster, coatings that are tougher, coatings that are more versatile. And that's what I want to talk about here this morning. All of you are familiar with certain textures. Velvet has a texture. The upholstery you're sitting on has a certain texture. But for somebody involved in materials, we have a little more technical definition of that. There are certain materials that have different properties in different directions. Wood is one example here. If you wanted to split this piece of wood, you know that you can do it relatively easy if you split it with the grain. Against the grain, however, it's very difficult to do. The aluminum oxide in CVD coatings has a similar property. It is harder in certain directions, it is tougher in certain directions, more wear resistant, it is denser, it's a better insulator in certain directions. And so for about the last 7 or 8 years in the scientific literature, people have said things like this: if you could figure out how to change the texture of the aluminum oxide layer in these CVD coatings, you could come up with a better product, something that lasts longer, more versatile, it's tougher, and all of that sort of thing. And that's what we've done using the technologies that I'm going to describe with the next few slides. We experimented with a variety of what I'm going to call textures. Now for a moment, imagine a deck of cards. And those cards are relatively thin, they have some width and length to them. But you can imagine those cards, if you wanted to split the deck, you can do it between adjacent cards. Let's build a coating out of those cards. Coating number one, we're going to build by just randomly throwing the cards into some mold of some sort. Coating number 2, 3, 4, and 5, we're going to orient the deck of cards in different directions. D is the important one, as you'll see as we go along. There, we're going to lay the deck of cards like this. So the cards are parallel to the insert itself, if you will, to the cutting surface. E, for example, is perpendicular to that. We have the coating orientation, the texture, going up like this. So we would have adjacent crystals, or those cards, stacked this way. And you can imagine that deck of cards and then taking a hatchet, wanting to split that deck of cards with a hatchet. It's easy to do if you drive that wedge between adjacent cards. But if you turn the cards 90 degrees and have them oriented this way, it's more difficult to crack them. The cards now, if they are flat like this, leave a flat surface on the top here. So when you're machining with that kind of a surface, this is actually a photograph of the top of a coating at about 40,000 magnifications. All right, I'm going to show you another picture of that random arrangement of cards. That's here. If you take a look at this, you'll notice that there are ridges, there are points, asperities, if you will. It's somewhat like flying over the Rocky Mountains. And if you look out of the airplane, you see the peaks coming up toward you and all of that. Imagine a chip sliding across that kind of a surface. There's going to be a lot of friction, a lot of drag, a lot of grabbing, and all of that. That leads to metal buildup. It leads to increased friction, to heat, and ultimately what we call cratering, dissolving the coating if the temperature gets too high. If we go back to this previous thing, these are more like the mesas in the southwestern part of the United States. The chip slides across the top of these crystals. There's less friction, less drag, less metal buildup, therefore less heat, and that gives you a better surface finish in addition to all of the other benefits that I described. And basically that's texturing in a nutshell. What we've done is to control the orientation of those playing cards to bring a harder, tougher, slicker, smoother surface into the cut. That means the coating is going to last longer, it's going to cut cooler, it's going to result in less metal buildup, which in turn is going to give you a better surface finish, less damage on the workpiece itself. If we use these different textures, again the important ones are A, in D and E, I'll say here for the purposes of discussion. A is the random orientation. You just took those cards, you threw them up in the air, and however they landed, now again, most of them are going to land like this obviously, but imagine for a moment that they were randomly organized and dispersed and arranged and all of that. That's what you have here, and that's going to be our baseline. D is where we control the texture so that the cards are like this. E is where they're like this. So any texture is better than no texture. This is no texture, no preferred orientation of those crystals at all. Okay? In cast iron, the difference in tool life, if we normalize this to 1, is not all that dramatic. You get maybe a 50% improvement in the life. All right, now that's something worth having. But if we get 50% in the laboratory, we assume that's going to translate to about 30% or 25% in real life. And you know, if somebody can come in and show you a 25% improvement in tool life, well, you're interested in that, but you don't jump up and down over it. If we go to steel, however, you can see that we can more than double the tool life with the controlled texture. And again, that's because it's tougher, harder, cooler, and all of the rest of the things that I talked about. Okay? And if we measure flank wear, the progressive dulling of the cutting edge, versus time in cut across the bottom, you can see that the coating that gives the best wear resistance is the one where those cards are like this. Okay? Again, it is cooler, better, and all of that sort of thing. The other ones are progressively worse. One of the peripheral advantages of this kind of texture is that we get rid of something called dislocations. Unless you're a metallurgist, you probably don't know what that means, but it's defects in the material. It's atom layers that are missing and things like that. All of these black lines, the fuzz, the cobwebby stuff in here, it renders the coating brittle. Less able to plastically deform with high heat and all of the rest. Cleaner structure with this textured coating. We didn't anticipate that when we did it, but a cleaner structure like this is tougher, it's more ductile, and more resilient and all of the rest. When we begin to machine with this, this texture that we're calling coating D provides better life. If you take a look at the edge here, very little wear. You take a look at the edge here, and at this point, this white layer, the aluminum oxide has been breached, it's been worn through, and you're exposing the titanium carbonitride underneath it. Now, I jumped into this whole talk a little bit too quickly. All of these coatings are identical in terms of thickness and composition. We start out with the exact same substrate, the exact same edge prep, the same coating thickness. We have 3 microns of titanium carbonitride topped by 8 microns of aluminum oxide. And it's that aluminum oxide texture that we're controlling. And on the coating on the right, you can see the aluminum oxide is worn through under these conditions, and this coating is still doing very well. Got a lot of life left to it. And if we dig in a little bit further, you can see that the way the coatings wear is different. And this is a key slide right here. These photographs taken of the tops of the inserts. So you're looking down. The chips were sliding from right to left in the direction of the arrow. This is the coating where the texture is like the playing cards laying down. That coating because it doesn't have the dislocations, is tougher, it's more ductile, it can deform plastically without cracking, and so it moves a little bit, it stretches. And what you see here, these marks, depending on where you're sitting and the light reflection and all of that, this is not metal that's smeared on the surface. After we did the machining, we put the inserts in boiling hydrochloric acid to remove all of the metal off the surface. So you are actually seeing the aluminum oxide sliding a little bit, deforming a little bit. Other textures, and this was the best of the others, but you can still see the cracks in there. And those cracks lead to chipping of the coating, which in turn leads to ragged wear, which gives you a bad surface finish and leads to metal buildup and further cracks, additional cracks, and all of the rest. You can see some of these cracks in here, but the thing I want to point out, there are flat facets. The chip control direction, or the chip flow direction, bottom to top here, on occasion you can see little chips coming out of this particular coating that's textured. Okay? But they're small. They're not very deep. It's like one of those cards being pulled off of the surface. Whereas if you have a different orientation, a different texture, this chip right here is much deeper. This is more serious damage, if you will. Okay? And so we want to avoid this kind of wear, get back to this kind of surface. What we'd really like to do is eliminate these kinds of chips altogether and only see plastic deformation on the surface of the aluminum oxide. Aluminum oxide is a ceramic, it's brittle, and so it's very difficult to get it to deform plastically as opposed to chipping. But if we can get the right texture, that will happen. What does this mean in terms of practice, in terms of something practical that you can use on the shop floor? Well, number one, the textured coating is harder. Now this does not go all the way to zero. I want to point that out. The textured coating is about 10% harder than conventional coatings. All right? Not only is it harder, but it runs cool. These are thermal images. I don't know if you can see the chip bending across the top. This is the insert itself. The tip of the insert is hot. You've got some heat underneath the chip and so forth. But the textured coating runs about 35 degrees cooler, and you say, well, that's not a whole lot when the numbers are this high, but it's enough to make a difference, enough to slow down what we call crater wear. In turn, that allows you to run faster, more productively. Okay? And in addition to that, one of these slides that I showed earlier, I've just put on a different slide here, but conventional coating, textured coating on the right, smoother, less heat, less friction, better surface finish, and all of the rest. And so that's the end of the slides. Just one other comment that I might make. A lot of times today people are running slower than what they could. You know, we make a certain brand of cutting tool inserts, but speaking for the cutting tool industry as a whole, I think we would prefer that users do run faster than what they are today. And if I can use one more analogy, if you're running at low speeds, the cutting edge is not very hot. If I live on a farm, if I go out to my barn and get a hard, brittle piece of steel, put it in my vise, put a pipe on that, and go to bend it, I'm probably going to fracture it, right? Because it's brittle. But if I take that same vise, same pipe, same piece of steel, but now get it red hot with an oxyacetylene torch, I can bend that rod without it fracturing. If we can get these coatings hot, they are tougher, more difficult to chip. You get smoother wear, less wear, more consistent tool life. So we think there are a lot of advantages to that. All right. Any questions? Yes?
Most people run at too slow of a speed. Yeah. What's the reason for that? Is it equipment, or they just don't know that they should be running it faster?
If you didn't hear the question, a lot of people are running too slow. Why? A lot of it is momentum. We've always done it this way. And one of the things that troubles us about that attitude is that if we don't change, somebody in China will, somebody in Mexico will, somebody in who knows where, Brazil will, and they'll get the work. So whenever we hear somebody say, we've always done it this way, it's always worked for us, we don't need to change, that's troublesome. Technology is constantly getting better. It's improving, not just from our company, but the cutting tool industry in general. but it's inertia.